Hi, my name's Jamar Bynum, and I'm the geology discipline lead for North America within Baker Hughes's Reservoir Technical Services division. And for those of you that don't know me, I'll give a little background on myself. I'm a geologist with a focus in carbonate and siliciclastic sedimentology and depositional systems modeling. My graduate studies were at Oklahoma State University, where I kind of focused on Devonian and Mississippian depositional systems within the mid-continent. And I had the opportunity to work with the late Dr. Boardman, and I'm currently working with Dr. Jack Passion. So I have a little over a decade of experience within the oil industry, and the majority of the time, it's pretty safe to say, has been spent at OPIC, hovering over core boxes. So I like to say I have a little bit of the initiation process of working at OPIC prior to the wonderful climate controlled conditions that are available down there now. So it's a wonderful facility. I also have a lot of gratitude for the OGS staff for putting up with all my tedious sampling requests and last minute layouts. And thanks to the OGS for the opportunity to present at one of the workshops again. I really enjoyed the last one I got to participate in with the STACK workshop. So I'm glad to be a part of the Shale workshop this time around. And so today we're going to kind of talk about unconventional reservoir modeling of Devonian strata in Oklahoma, and really focus on utilizing the rock volatile analysis. So this is a project that's kind of in collaboration with Baker Hughes and advanced hydrocarbon stratigraphy, which Mike Smith gave a great talk on yesterday. So this is kind of like a bolt-on to his talk. And just to give you kind of an idea of where we're going to be going in the talk, I'll kind of show some location maps, go over some brief geologic background, and discuss some of the structure and reservoir characteristics. And then we'll take a look at the VAS methods and data sets, and then kind of get into these 3D visualizations of those data sets, and then go over a few concluding points. So the project area we're discussing today is located kind of in southeast, south central Oklahoma, in the western part of the Arkoma Basin. And so the area of interest is indicated by the yellow star and is located in Cole and Hughes counties. So locally within the basin, we're bounded to the west by the Arbuckle Uplift, to the north and east by the Cherokee Platform and the Ozark Uplift, and then to the south by the Ouachita Mountain Front. And so the area of interest is kind of located in this very structurally complex area where we have some large normal faults producing a series of horsts and grabens that can create some pretty difficult challenges drilling condition wise, with the major faults producing hundreds of feet of throw and abundant smaller faults producing tens of feet of offset. And so this structural regime is a result from the Pennsylvania Ouachita orogenic event. And so we've had some talks yesterday and some great ones today that, really dove into the depositional details of the Woodford Formation, but just a few key points on the geologic background to kind of keep in mind while we go through this talk. So on the right, we have a paleogeographic rendering by Blakey of the late Devonian, so around 360 million years. And the project area is indicated by the white dot. And so we have these Devonian source rocks and unconventional targets that are present across North America's largest hydrocarbon producing basins, from the Appalachian Basin in the east to the Permian Basin in the west. And so during this time, we're really positioned around 20 degrees south latitude on the western margin of the Laurentian continent. And a good modern analog to the oceanographic conditions would be kind of the west coast of South America or Africa, where we find these large upwelling currents producing nutrient-rich waters, which in the Devonian were feeding these silicious radiolarians and algae-rich blooms that give us the famous chert beds of the Woodford. So below our paleogeographic map, we have our Arkoma Basin stratigraphic column. And as we discussed yesterday, the Woodford Formation is late Devonian to early Mississippian in age, and is equivalent to the Arkansas novaculite that's deposited in the eastern section of the basin. So on the left, we kind of zoom in on a gamma ray type log for the Woodford Formation, which can exhibit API units ranging from 100 to 650. And so traditionally, the formation is kind of broken into these three informal members that have been discussed as the upper, middle, and lower. However, within the industry, most operators tend to have their own nomenclature and divisions. And so in general, though, the lower gamma ray intervals contain higher concentrations of silica-rich facies, while the higher gamma ray intervals contain facies enriched in TOC, phosphate, and clay mineralogies. So now if we kind of take a look at a few of the Woodford reservoir characteristics, in the project area, drilling targets were set near those cooler gamma ray packages. So taking a look at some of the core within the cooler targets, we see these interbedded silica-rich mudstones with TOC-rich mudstones. And so the silica-rich mudstones have a very distinct texture and blue color to them, and were highlighted in the core photo by the red brackets. And then the photomicrograph on the right allows us to see what the constituents of the silica-rich beds are. And they're dominated by these tasmanides, which are the preserved silica-rich bodies, if you will, of the algae, and the radiolarians, which are these single-celled organisms with siliceous skeletons as well. So our silica-rich interval is
Jamar, are you still there?
Yes, can you hear me? Sorry, I think my I think my internet kind of dropped it a little bit. Can you guys hear me now?
We can.
Yes.
Go ahead, Jamar.
Okay, sorry about that. So I'm not sure where I dropped off at, but we have these radiolarians and algae that are real silica rich. And so these intervals are dominated by this biogenic silica rather than detrital quartz, which can be kind of tricky when interpreting XRD results across different areas where the Woodford's targeted. So for example, when you're moving up dip onto the Cherokee platform or the Anadarko shelf, the abundance of these biogenic silica beds kind of decrease, due to depositional environment constraints. But when you're looking at the XRD, the quartz is being reported in similar quantities. So this is kind of a due to a switch in biogenic silica to detrital quartz dominating the sediment. And that can have some effects on production. So it's kind of important to keep that in mind as well. And also the biogenic silica-rich beds contain bed-confined fractures, which are demonstrated by the red arrows in the core photo. And so this is indicating that these silica-rich beds behave more brittly than the other Woodford facies and potentially aid in migration and production of hydrocarbons. And so now we're going to kind of move over to the data sets that were used in the modeling and visualization. With this project, we had a unique opportunity to really integrate our RNS and VAS data sets. So Baker Hughes provided the client with both drilling and geosteering of their wells. And so our reservoir navigation service team was able to provide the well surveys and trajectories, the formation tops, target zone information, And also, the gamma ray that was captured along the lateral while drilling, and some key structural observations that were made too. Additionally, data was provided by the client, and it included, a couple of different 2D grids of significant surfaces and offset well data that included some surveys and logs as well. And this kind of provided the backbone of the model we're going to take a look at. So then I started working with Mike and Chris at AHS with the VAST data. And we kind of had this goal in mind to create a 3D visualization of the geochemical signatures of the fluids in the reservoir. So in the area, both sealed it well and lab loaded data sets were available. However, to make sure we were staying consistent, we decided to utilize data sets with the same method so that we didn't, compare older cuttings to sealed at well samples, and just make sure that everything that was consistent. So going forward, we decided to go with the sealed at well samples. And now one of the most interesting parts of the VAS analysis is the amount of data you can really get out of the cuttings. And, this is typically an underutilized source of reservoir information. So while there's different rock volatile properties we can take a look at, the ones we're going to kind of focus on today are going to be the total gas volume, the total oil volume, permeability, mechanical strength, acetic acid, and the toluene and benzene ratios. Also, we're going to go through the visualization. Keep in mind that there were 4 wells that were analyzed, and 2 of them were sealed at well and 2 were the lab loaded. So we're going to focus on those 2 sealed at well, at the well. And then we're going to also need to remember that as you go away from those wells, your geologic uncertainty is going to increase in the reservoir model. Okay, so there are 2 different sampling methods, the lab loaded and the sealed at well. The lab loaded method involves crushing the cuttings samples at the start of the extraction process. And this method provides the opportunity to run VAS on older cuttings from legacy cores or drilled and uncompleted wells an operator might have in an area. And it also provides an opportunity to conduct post-mortem assessments on particular wells that may have underperformed or things like that. Then there's the sealed at well method, which involves extraction without crushing the sample. And this method provides an opportunity to preserve the downhole reservoir fluid conditions a bit more detail. And then the lab loaded, it also provides a dynamic insights on the fluid migration and charging effects related to faulting. So for any particular project, the sampling method and collection intervals are customized to, different project specific needs. And Mike and Chris stay very engaged with the clients for project planning stage all the way through the interpretation process. So they provide excellent recommendations and guidelines for the sample collections. One of the basic recommendations though for all the projects is to capture samples above the reservoir in the vertical so we can establish the baseline geochemistry of the hydrocarbon system. Then really deciding on whether you want to run the sealed at well or the lab loaded is kind of dependent on the scope of work for the project and the real lateral and vertical level of investigation that's needed. So the table on the right is the data we're discussing today. There were 4 different wells. 2 were analyzed by sealed at well and 2 with the lab loaded. The sampling intervals for the lab loaded wells were wider during the collection process. So one sampled every 100 feet in the vertical and 300 feet in the lateral, while the other sampled 400 feet in the vertical and 100 feet in the lateral. The 2 sealed sample wells had a tighter sampling interval and chose to focus on the visualization. So well 1 was sampled at 10 feet in the vertical and 90 feet in the lateral, while well 2 was collected every 30 feet in the vertical and then similar in the lateral with 90 feet. So we were able to kind of have, with one of the things that the client wanted to, utilize was kind of testing, well, sealed at well versus lab loaded. And so with well one, they actually chose to analyze in both methodologies, the sealed at well and the crushed lab loaded. And so one of the outcomes when comparing the two data sets is that there's a little different analytical approach or a mindset when it comes to interpreting the data. The two property logs on the right are from the same well, well one. The top log suite represents the sealed at well, while the bottom represents the crushed lab loaded samples. When viewing the logs, it's good to kind of orient yourself as to where you're actually looking at downhole. So for example, the heel of the lateral is located on the left portion of the property log. And as you move to the right, you're going down the lateral towards the toe of the well. Also, for a little extra information that was provided by the Baker Geosteering team, while drilling, the yellow lines are indicating where they cut faults in the well. A few of the points we can recognize when comparing the methods are that the sealed at well samples provide more detailed insight into the lighter hydrocarbons and the total gas property, and it captures and retains vast properties used for interpreting open faults migrating fluids. And another point is that when the lab loaded method is used in tandem with the sealed method insights, we can provide some insight into water versus oil wetting intervals. Okay, and so on this slide, we can see that on the right, we have the property logs for well 1 and 2, which are the sealed at well method. And they were the ones that were chosen in the visualizations that we're about to dive into. So a few key points that stick out are when comparing the two wells, well 1 was drilled through a more geologically complex area where we're cutting a lot more faults that have larger offsets. And also, we see indications of faults affecting fluid migration and hydrocarbon charging of the fault blocks. And then well 2 was drilled in an area that would be indicative of less production potential when compared to well 1, with low proximity to pay indicators and low relative permeability. So there's also this high total gas zone, which is interpreted to indicate tighter reservoir rock. And so now we're going to take a look at this visualization, and to just get you kind of oriented, here's the area that we're going to take a look at. You can see that we have quite a few faults. There's 7 main faults. And so this would be what I'm going to refer to as the southern fault block. And then this is the northern fault block. And then there's a series of graben fault blocks down here. And so the first property that we're going to take a look at is permeability. And it's important to remember that the permeability measurements are relative and qualitative, that they're not quantitative. And so when we take a look at what we got from well 1 and well 2 analysis, we see that the northern upthrown fault block contains the lowest permeability in the area, and that the highest permeability measurements are kind of captured in these highly faulted areas. So fault block 5 and 6, 4, and then around this southern fault block around this large offset. And so this is kind of zoomed in on well 1, this lower left figure. And you can see that the warmer colors are indicating where we have higher permeability, and then the cooler colors are indicating where we have lower permeability. And so you can see, like, when we hit this, we go way out of zone and our permeability drops way off, but then we start getting back into the Woodford, and we're getting back our higher permeabilities. Next, we're going to take a look at the toluene and benzene property. And this provides insight into oil migration. And so values that are greater than 3 are indicating that there's significant migration occurring. The cooler colors represent lower values. And so basically wherever we're seeing, you know, kind of this yellow to orange or red, we're getting above values that are 3. So we have migration occurring. And we can see that the highest concentrations are kind of around this fault 7 that has large offset. And then the zones within the graben that have the highest offset as well. So fault 5 and fault 3. And then when we kind of zoom in, you can see this a bit better. This is well 1. And so you can see at fault 5, we get these warmer colors coming back in, higher values of that ratio. And then around fault 3 and then this large fault 2, we can see that there's migration occurring around it as well. And then now we're going to take a look at the acetic acid property. And this provides insight on proximity to pay. And it's basically related to the biodegradation of hydrocarbons. So our highest values are the warm colors, and they're really picking up in the graben fault zone and then right along the large southern fault block. And so we can also see when we kind of get into well 1 closer looks that we're actually getting like higher proximity to pay and production potentials within the graben fault zone. So now we're going to take a look at mechanical strength. And these values range between 0 and 2. And they're produced by mechanically squeezing the cutting tubes that are analyzed. And so we can see that we get pretty consistent measurements across the Woodford and that there's high mechanical strength. So when we think back to, you know, the Woodford and all those chert-rich beds, that's making sense that that's what we're seeing. The lowest mechanical strength readings are occurring when the borehole's going out of the target zone. And so if we look at this zoomed in section, we go out of zone right here with this large fault 2 offset and trying to get back in. And then once we get back into it, we start getting our higher mechanical strength readings, and then we kind of drop out of zone a little bit again at the toe.
Excuse me, Jamar, you have about 5 minutes left.
Perfect. And now we're going to take a look at the total gas volume. And we can see the volume recovered is pretty consistently low within the graben and the southern fault block. This low gas volume recovery from the cuttings is potentially indicating that we have better gas production areas due to those open faults. And then the northern fault block zone is exhibiting this high gas volume where we're getting minor faulting, and it kind of, we're thinking that it provides a better representation of the gas in place within the reservoir. And here's the total oil volume recovery, and we can see that it's definitely lowest to the north, and then where we're drilling out of target. And then our higher oil volumes are in the recovery zones due to open faults migrating hydrocarbons. And so the oil volume indicators within well 1 lateral are occurring along interpreted faults from where we saw those toluene and benzene ratios getting up above 3. And this is further evidence for migration. And so you can see where we start diving into low total oil is where we're either out of zone or the faults aren't contributing. So we're out of zone, out of zone. And so just a few concluding points are that sampling interval and method are really dependent on the scope of work for a specific unconventional reservoir and project area. So the new wells are open to the sealed at well sampling method. And then legacy wells or ducts are open for our lab loaded crushed method. And that if you're wanting to kind of put together a 3D visualization of the VAS data, it really requires a consistent sampling method across your area of interest. And then the 3D VAS visualizations offer detailed insights into the reservoir fluid conditions with unconventional reservoir targets. And so we can kind of take a look at single wells analyzed and produce a 3D visualization of the VAS properties and how they're distributed along the wellbore and insights into the reservoir quality. Or we can put together a multiple well analysis and provide insight for the 3D reservoir modeling with respect to the VAS properties and kind of get a better idea of the relationship with the overall geologic framework of an area. And a few key things that we saw from the unconventional Woodford and the Arkoma here is that it's dependent on the geologic complexity and mapping of these open faults, migrating and charging designated fault blocks with hydrocarbons. And then that the reservoir quality insights from VAS show that proximity to pay and permeability indicators are highest in those graben fault blocks. And so that is all I have to share, and I would love to discuss things further with everyone.